Hi everyone. So we're starting a new unit today, and this unit is mainly the main topic of the unit is integration. And basically what we've been doing for the entire course is we have been going in one direction, and that direction is from a function to its derivative. We have been differentiating. And in this last unit on integration, what we're going to see is that we're going to go in the opposite direction. We're going to go from a derivative back to the original function. And that process is called integration. And in the first part of the unit, we're going to go through a lot of the mechanics of integration. And then in the second part, we're going to go through a bit of the theory behind integration and how it actually theoretically connects to differentiation. Okay, so today we're just going to get into sort of the beginning pieces of integration. And let's just start with any function. Okay, so let's say we start with something really simple, a polynomial function. Let's say we start with something like f of x equals x cubed. Okay, and now let's say that we take a derivative and end up with this function, f of x equals x cubed. And we want to know, well, what was that function that we took the derivative of to get the derivative f of x equals x cubed? What was the original function? If f of x equals x cubed is the derivative, what was the original? Okay, well, we know from the power rule that if you're taking a derivative, the exponent goes down by 1. Okay, so that's one thing we know. So I'm going to call this original function capital F of x. We know that it would have had to have an x to the 4 in it. Okay, now the other thing that we know is that when we take a derivative, this 4 would have had to come out in front. Okay, we would have had to multiply by 4, but the coefficient of this derivative f of x is just a 1. So if we had multiplied something by 4 to get a 1, well, this original coefficient must have been 1/4. Okay, now we know that that was in there, but we also could have had a constant, because remember that the derivative of constant is 0, and so that's not actually going to show up in the derivative. So we don't know if there was actually a constant present in the original function. And so we have to include that in this original function, just in case there was. Okay, now we can always check this, right? If f of x equals 1/4 x to the 4 plus c, right? Actually, I have this down here. Then what would f prime of x be? Well, it would be 1/4 times, I'd have to take the exponent and multiply by that, so that's 4, and then decrease the exponent by 1. And then the plus c would just disappear, because remember the c is a number, it's a constant. So let's say it was plus 5, derivative of 5 is 0. Okay, now when we simplify this, 1/4 times 4 is 1. So this just becomes x cubed. Okay, and we're going to get into, this isn't always a guessing game. We're just sort of exploring a little bit right now, but we will go through like a process of how to get, this is actually called an antiderivative. Okay, so when we're going in the opposite direction, we are finding an antiderivative. Okay, now why would we want to know an antiderivative? Well, if you know the derivative, but you don't know the actual function, then you can get back to the original function. Okay, so that's one reason. And there are lots of applications where this could come in handy. So I'll just give you an example of one, and we'll look more at this next class. When we were doing applications of derivatives, we looked at particle motion, right? We looked at position, velocity, and acceleration. And we saw that velocity was the derivative of position and acceleration was the derivative of velocity. Well, what if we know velocity and we want to know position, right? So then we can work backwards and find the antiderivative of velocity to find the position function. Okay, now there is a special name and notation for an antiderivative, and it's called an indefinite integral. And it looks like this, and we would read it this way. The integral of f of x dx is equal to capital F of x plus c. Okay, so in the example that we just looked at above, we would write it this way. The integral of x cubed dx equals a quarter x to the 4 plus c. Okay, so this part is like the derivative. Whoops, my pen just conked out. And this would have been the original function. Okay, now it's called an indefinite integral because it's not definite, and that's because of this value c, right? We don't actually know what the constant is. And so the function, a quarter x to the 4 plus 1 is different than the function f of x equals a quarter x to the 4 plus 10, right? And so we actually get a family of functions from each indefinite integral. So when we don't know what that c value is, it's called an indefinite integral. Okay? All right. So let's find the general antiderivative of some of these functions. Now, the power rule, the reverse of the power rule comes up quite a bit. So let's actually just work with that a little bit. Okay? So when we are differentiating, right? If we have f of x equals x to the n, then f prime of x equals n times x to the n minus 1. Okay, so that's the process that we go through when we are differentiating. But if we start with f prime of x equals x to the n, and we want to go the other way, well then f of x, as we just saw above, the n has to now become n plus 1 because the exponent on the original function is always 1 more than the exponent on the derivative. So the exponent's going to be n plus 1. And then the coefficient of f of x has to be 1 over n plus 1. Because if you work towards the derivative, right, then if we took the derivative, we would multiply by n plus 1. So n plus 1 over n plus 1 gives the derivative function a coefficient of 1. And then the n plus 1 would decrease by 1 to get x to the n. Okay? And so this is how we work in reverse. And this comes up quite a bit. So this is just kind of handy to know so that you don't have to keep thinking through it every single time you integrate something that has power. Okay? All right, so let's say we are looking at this function. Well, firstly, I'm going to write this with a negative exponent. So this is equal 10 to x to the negative 9. And now when I take the integral of 10x to the negative 9 dx, that's going to equal 10 times, well, now the x, the exponent is going to be 1 more than negative 9. That's negative 8. And then I have to multiply by 1 over that exponent, plus c. Okay? And then I can simplify that a little bit, right? So 10 over negative 8 is negative 5 over 4 x to the negative 8 plus c. And you might also write that as negative 5 over 4x to the 8 with a positive exponent plus c. And the adding the c is very important because we do not know what the original function was, right? And that original function could have had any number added to it because the derivative of a number is 0. And so this plus c must be in there. And if you don't add that in there, then it's actually incorrect. Okay? All right, let's look at a couple more examples. Okay, so we've got a couple more polynomial examples here. So here's another polynomial. Okay, so here we're looking at f of x equals 6x squared minus 8x plus c. So if we want to find the antiderivative of this function, then we would be, and by the way, it is common practice to label the derivative function with a lowercase f of x and the antiderivative with an uppercase f of x. So that's what I'm going to do right now. F of x is equal to the integral of 6x squared minus 8x plus 3 dx. And we can basically just apply the rule that we just looked at a moment ago, the reverse of the power rule, one term at a time. Okay, so the 6x squared is going to be 6, and then the x will become x cubed, and we have to multiply that by 1 over 3. Okay, and then minus 8, the x is going to become x squared times 1 over 2. And plus 3x to the 1, and that would be 1 over 1, so I'm not going to put that in there, and then plus c. And then we would simplify these fractions, right? So 6 over 3 is 2x cubed, and 8 over 2 is minus 4x squared plus 3x plus c. Okay, so that is our capital F of x. All right, now for something like this next example, what you want to do for sure is divide each term by x, right? So this is the same as x to the 4 over x plus the square root of x over x. And remember, the square root of x is x to the 1/2 over x minus 3 over x. Okay, and that can be written as x cubed, and then x to the 1/2 divided by x. A half minus 1 is negative a half. So that's plus x to the negative 1/2. Whoops. And then this minus 3 over x. Now we have to remember that the derivative of ln x is 1 over x. So when you have the derivative with a power of x of negative 1 or 1 over x, the original function would have been ln x. So that's kind of the only exception to the rule. Okay, so here, if y equals ln x, then y prime equals 1 over x. Okay, and if we're working backwards, this is our y prime. So the minus 3 over x is our y prime. We're working back to the y. Okay, so to get our f of x, we want to take the integral of these three terms, x cubed plus x to the negative 1/2, and then minus 3 over x dx. Okay, so one term at a time. The x cubed is going to be x to the 4 times 1/4 plus the x to the negative 1/2. So we have to add 1 to the negative 1/2. So that's going to be x to the 1/2 times 1 over 1/2. And then the minus 3 over x is minus 3 ln x. Okay, and then of course we can simplify the first two terms a little bit. So I'm just going to write this as x to the 4 over 4. And then 1 divided by 1/2 is 2. So plus 2, and then maybe I'll write square root of x minus 3 ln x. Okay, so that's like our capital F of x. Okay. All right. Here's another one. F of x equals the square root of x plus the cube root of x. So just like when you're finding derivatives, when you're looking at integrals or antiderivatives, convert your radicals into fractional exponents. So this is x to the 1/2 plus x to the 1/3. So here we're looking at f of x equals the integral of x to the 1/2 plus x to the 1/3 dx. And remember, we have to add 1 to the exponent and then divide by, or go 1 divided by that new exponent. So it's going to be 1/2 plus 1 is 3 over 2 times 1 over 3 over 2 plus 1/3 plus 1 is 4 over 3. So x to the 4 over 3 times 1 over 4 over 3. Oh, you know what I've been forgetting? You know what I forgot to do on the last one? I'll do it now. Plus c. Let me erase. I forgot on this one. I forgot to put in a plus c here. I told you guys not to do that, and then I did it myself. There we go. Okay, that's better. Okay, and then I'm going to fix the just coefficients up a little bit, right? So 1 divided by 3 over 2 is 2/3. So this is 2/3 x to the 3 over 2. And then 1 divided by 4 over 3 is 3/4 plus 3/4 x to the 4 over 3 plus c. There. I remembered the c that time. There we go. Okay. All right. Let's look at another one. So here we've got the integral of 3 over x plus e to the x dx. So there we have the like something over x, right? When we have an exponent of -1 on x, or a 1 over x, or a number over x, you have to remember that bit about ln x. Okay, so this is going to essentially equal 3 ln x plus, and then remember the derivative of e to the x is e to the x. So if the derivative is e to the x, the original function would have been e to the x as well, plus c. Okay, so that would be the integral or the antiderivative. Now, one thing that we should talk about with the ln x, and actually we could have talked about it earlier when we did it in the first example, but I'll talk about it here. I have a little bit of room, is that you have to consider domain, right? So this function over here, the integral, only has a domain of x greater than 0 because you can't take the ln of a negative value. Whereas the derivative, 3 over x plus e to the x, basically has a domain of anything except for 0, because we're dividing by x, right? So x can't equal 0, but it can equal anything else. Okay, so if we want the domains to match, then all we need to do is this. Stick some absolute value symbols around the ln x, and then these two domains will be the same. Okay? All right, next one. Here we're looking at trig functions. So one thing we need to remember about trig functions is that if you start with sine x, the derivative is cosine x. If you start with cosine x, the derivative is negative sine x. So when we're working backwards, we have to remember that, okay? All right, so in terms of getting the original function back when we're integrating, If the derivative is cosine, the original would have been sine. So derivative of 3 cosine t is going to be 3 sine t. And if the derivative is negative 4 sine t, right, the negative is already there, the original would have been positive 4 cosine t. Okay, because the derivative of cosine would have made the negative sign, would have put the negative sign in there. And then, of course, plus c. Okay? All right, so those are indefinite integrals. Now, sometimes you have some conditions where you may actually be able to figure out the specific functions. Okay, so for example, find the curve y equals f of x that passes through the point 2, 3 and satisfies this dy dx, the derivative, equals 12x squared plus 4x plus 1. Well, now we actually have a point on the curve y equals f of x. So once we find the original function, we can use that point, and we'll find that original function using the derivative and integration. Then we can use that point that we know to get the actual c value and get the specific function that satisfies these conditions. Okay, so the first thing that we need to do is figure out the integral. Okay, so f of x is going to be the integral of 12x squared plus 4x plus 1 dx. Okay, so this is going to be 12x cubed times 1 over 3 plus 4x squared times 1 over 2, and then plus x, right? Derivative of x is 1, and then plus c, of course, right? So simplifying, this becomes 12 over 3 is 4x cubed, plus 4 over 2 is 2x squared, plus x plus c. So this is f of x, capital F of x. Now we know that f of x passes through the point 2, 3. So we can plug in a 3 for f of x and a 2 for x, and then we can solve for c. So that's what I'm going to do next, right? I'm going to plug in 2, 3 to get c. Okay, so that would give me 3 equals 4 times 2 cubed plus 2 times 2 squared plus 2 plus c. Okay, and then that's 3 cubed is 8, so 32 plus 2 squared is 4, 4 to 8 plus 2, and that's 32 plus 42 plus c. So that means c has to be negative 39. Okay, so what is the actual function f of x? It is 4x cubed plus 2x squared plus x minus 39. Okay, all right, one more question. Now I have to fix the wording of this question a little bit because the wording is a little messed up. So find the function with a derivative of that passes through this point. The wording parallel to actually doesn't make sense here, because if it was parallel to the derivative, it would just be that same exact derivative function plus a constant. Okay, so sorry about that wording, just cross that out on your notes. And this should say, find the function with the derivative of dy dx equals 1 over x plus e to the negative x that passes through this point. Okay, so very, very similar type of question, but we're dealing with a slightly different type of integral because this is not a polynomial function. Okay, but we still have to start out by getting our capital F of x, and that is going to be the integral of 1 over x plus e to the negative x dx. Okay, and that is going to be, remember, the derivative of 1 over x is ln x. And then the derivative of e to the negative x, well, if e to the negative x is derivative, the original function would have been e to the negative x. But to make it plus, right, when you're taking the derivative, you also would have had to multiply that by -1. Because you would have had to apply the chain rule. So this actually has to be a minus e to the negative x. And if you're thinking about why, then work backwards, right? So I'll maybe put that off to the side. Think about taking the derivative. It would be the derivative of ln x is 1 over x, and then minus e to the negative x times the derivative of negative x, which is -1. And then derivative of c is just 0. And that makes 1 over x plus e to the negative x. So that's why this has to be negative. Okay, so you know, it takes some time to practice these kinds of things. And to get used to them. But one thing that you can do that's actually quite a useful exercise to go through because it will help you. Actually, you know what I forgot? I forgot the absolute value symbols. Is to actually go backwards, like try it out. Is this the integral? And then make sure that if you go the other way, you end up with this, right? And if you don't, then you may have a sign error in there. And you can kind of work it out that way. And going through that process actually helps you to intuitively be able to figure out what's going to happen. Okay, so what we have is f of x equals ln absolute value of x minus e to the negative x plus c. Okay, and we know that it passes through the point 1, 0. So we can plug that in and solve for c. So that's what I'm going to do. I'm going to plug in a 0 for f of x and a 1 for x. Okay, and then we have to think about what is ln of 1. Well, ln of 1, right? Remember this has a base of e. So we're trying to figure out e to the what equals 1. Well, the only exponent that's going to give you a value of 1 is 0, unless the base is 1, of course. So ln base e of 1 is equal to 0. So this first term is actually 0, which means that c equals e to the negative 1. And now that we have the c value, we can say what the actual specific function is. And that function is f of x equals ln absolute value of x minus e to the negative x plus c. Plus, what am I saying? Plus e to the negative 1. There we go. All right. I think I'm going to leave it there before I make any other mistakes. But I'll see you guys again.